You think you know Schrödinger? Wave equation, dead cat, Nobel Prize? Everyone knows that story. But what if the man who gave us the mathematical heart of quantum mechanics spent 30 years fighting the very interpretation everyone thinks he believed? What if probability was never his answer? What if his understanding was so radical that physicists are still wrestling with it today? The equation changed everything. The man behind it rejected almost everything that came after. In 1962, in Mikhail Bitbol's detailed philosophical analysis in Schrödinger's Philosophy of Quantum Mechanics, published by Springer in 1996, which examines unpublished correspondence and working papers from Schrödinger's estate in Vienna. Now back to the information. 3 languages before age 10. His father runs a linoleum factory. His mother comes from chemistry professors. The family apartment overlooks the Ringstrasse. Books everywhere. The boy reads Schopenhauer at 14. That philosopher will haunt him for life. Schopenhauer worshipped one text above all others, the Upanishads, ancient Sanskrit writings, 2,500 years old. Erwin absorbs them through German translations. The core idea sticks. What we see is representation, not reality itself. The world is one consciousness appearing as many. He never lets go of this thought. Erwin finishes his doctorate on electrical conductivity in moist air. Unremarkable work. He bounces between positions. Breslau, Jena, Stuttgart. World War I interrupts. Artillery officer on the Italian front. Survives, returns to science. 1921, University of Zurich calls. He's 33. Still hasn't made his mark. Max Born and Pascual Jordan extend it. Matrices, multiplication that doesn't commute. Position times momentum is not momentum times position. The math works, but nobody can visualize it. Paul Dirac in Cambridge sees the structure, develops his own version, 3 separate formulations of something new, but what is it describing? Nobody can picture it. He's recovering from tuberculosis, takes his mistress, not his wife. The details stay murky. He brings physics papers. Louis de Broglie's 1924 thesis, matter has wave properties. If light can be particles, maybe particles can be waves. The wavelength equals Planck's constant divided by momentum. Schrödinger sees something. If electrons are waves, they need a wave equation, not matrices, actual waves. Returns to Zurich with the answer. January 27, 1926. He submits his first paper to Annalen der Physik. Title, Quantization as an Eigenvalue Problem, Part 1. The paper introduces what we now call the Schrödinger equation, a partial differential equation. Second order in space, first order in time. The solution is a wave function, symbol psi. He applies it immediately to the hydrogen atom. 1 electron orbiting 1 proton. The bound state problem. Discrete energy levels. He uses advanced complex analysis, the Laplace method, learned from mathematician Ludwig Schlesinger's differential equations textbook. The calculation is brutal. Spherical coordinates, separation of variables, radial and angular parts. 3 quantum numbers emerge naturally. Principal quantum number n equals 1, 2, 3. Angular momentum quantum number L. Magnetic quantum number m. The energy depends only on n. The formula matches Niels Bohr's 1913 model exactly. Energy equals negative 13.6 electron volts divided by n squared. Perfect agreement. But Schrödinger derives it from a wave equation. No arbitrary postulates, no quantum jumps, just waves. All in 1926. A complete reformulation of quantum theory in 6 months. He proves his wave mechanics is mathematically equivalent to Heisenberg's matrices. Same predictions, different language. Born and Jordan immediately recognize the power. Heisenberg hates it. Too visualizable, too classical. But experimentalists love it. You can calculate things, spectral lines, transition rates, chemical bonding. The wave function becomes the central object in atomic physics. Max Born publishes a paper on collision theory. Born is 43, professor at Göttingen, Heisenberg's mentor. Born sees a different meaning in PSI. He writes it in a footnote, page 865, in Zeitschrift für Physik, volume 37. The wave function squared is a probability density, not charge. Probability. The probability of finding the electron at position x, y, z when you measure it. 1 measurement, 1 electron. Not a spread out cloud, a particle that could be anywhere, with probabilities given by psi squared. This is the Born rule. It becomes the standard interpretation. Nobel Prize in 1954 for this single insight. Electrons arrive at detectors as points, not as fractions. Quantum jumps happen. Energy transitions are discrete. His continuous wave picture can explain the clicks and Geiger counters. By October, he visits Copenhagen. Bohr argues with him for days. The debate runs from breakfast through dinner. Bohr insists discontinuity is fundamental. Measurement collapses the wave function. One outcome emerges from many possibilities. Schrödinger leaves exhausted, writes to Bohr afterward. Psychological impact is greater for me than for you. He concedes defeat, but never truly accepts. The measurement problem crystallizes. Einstein proposes thought experiments. Bohr responds each time. Heisenberg presents his uncertainty principle in March of that year. You cannot simultaneously know position and momentum precisely. The product of their uncertainties is bounded below by Planck's constant divided by 4pi, fundamental limit, not experimental imprecision, nature itself. Schrödinger doesn't speak much at Solvay. His wave interpretation is already slipping away. His philosophical foundation, Schopenhauer, Vedanta, the unity of consciousness, conflicts with probability and measurement. In his private thoughts, he never reconciles it. You immediately know something about the other, but they're separated. No signal can travel faster than light. Therefore, the property must have been real all along. The wave function doesn't describe reality completely. Einstein writes to Schrödinger in June. Schrödinger responds enthusiastically. Finally, someone sees the problem. He calls the probabilistic interpretation quite ludicrous in private letters. July 13, 1935. He writes to Einstein about reactions from Born, Pauli, others. He compares their responses to someone saying it's cold in Chicago and another answering that's a fallacy, it's hot in Florida. Schrödinger sees the disconnect. Title: The Present Situation in Quantum Mechanics. In these papers he introduces what becomes his most famous contribution, not to physics, but to philosophy: the cat thought experiment, a cat in a steel chamber, a Geiger counter, radioactive atom, tiny amount, 50% chance of decay in 1 hour. If it decays, the counter triggers a hammer. The hammer smashes a flask of hydrocyanic acid. The cat dies. If no decay, the cat lives. Quantum mechanics says the atom is in superposition, both decayed and not decayed. Therefore, the entire system, atom, counter, hammer, flask, cat, is in superposition, both alive and dead. Schrödinger calls this quite ridiculous. He writes the PSI function of the system contains the living and dead cat mixed or smeared out in equal parts. He doesn't believe this describes reality. The thought experiment is meant to show the absurdity of applying quantum superposition to macroscopic objects. It's a reductio ad absurdum, not an endorsement. Charge of gunpowder plus cat in a box. Einstein changes the details, gunpowder instead of poison. But the point stands. Schrödinger and Einstein are intellectual allies against Copenhagen. They want reality to exist independent of observation. They reject probability as fundamental. They believe the wave function is incomplete or misunderstood, not the final story. Schrödinger flees Nazi Germany in 1933. His opposition to fascism is immediate. He leaves for Oxford. Then, after difficulties, his unconventional personal life, living openly with both wife and mistress, he moves to Graz, Austria in 1936. The Anschluss happens in 1938. Nazis annex Austria. He flees again, eventually settles in Dublin. Ireland stays neutral. He's safe. The Institute for Advanced Studies in Dublin becomes his home for 17 years, 1939 to 1955. Erwin Schrödinger, Francis Crick, James Watson all read it. Watson says it influenced his move into biology. But the final chapter discusses consciousness. Vedantic ideas appear openly. The multiplicity of minds is an illusion. There is only one consciousness. This from a Nobel Prize-winning physicist. A series of papers and lectures. Are There Quantum Jumps? Published in British Journal for the Philosophy of Science in 1952. 2 parts. He argues against discontinuity, against measurement collapse. He proposes returning to something like his original 1926 interpretation, but more sophisticated. He's studied philosophy for 25 years since then. His position now: the wave function is not just a calculational tool, it represents something real, but not a physical wave in space, not probability in the Copenhagen sense, instead a representation in the Schopenhauerian sense. The wave function encodes all possible observations without claiming particles have definite properties before measurement. But it's not ignorance about existing properties. It's that the questions themselves are undefined until measurement creates the context for an answer. This is subtle, different from Copenhagen, different from hidden variables, different from many worlds, which Hugh Everett won't propose until 1957. Schrödinger is trying to thread a needle. Objective wave function, no collapse, no probability is fundamental, but still agreement with experiments. By 1950, Copenhagen is dogma. Bohr is revered. Einstein is dismissed as senile, fighting battles he's already lost. Schrödinger is seen the same way. Brilliant past, confused present. Most physicists follow what David Merman later calls, shut up and calculate. Don't ask what it means. Just compute predictions. Compare with experiment. Foundational questions are philosophy, not physics. This attitude dominates for decades. What was Schrödinger actually saying? Look at his philosophical sources. Arthur Schopenhauer, 19th century. Schopenhauer claimed the world is representation. What appears to us is not the thing itself, but how it appears to minds like ours. Behind appearances is will, a single unified drive. No multiplicity there. We perceive many objects because that's the structure of representation. Space, time, causality, these are forms of our perception, not properties of ultimate reality. Schopenhauer got this partly from Immanuel Kant, partly from the Upanishads, which he read in Latin translation. The core teaching, Atman equals Brahman. Individual self equals universal self. The appearance of many separate consciousnesses is Maya, illusion. He writes in his 1956 lectures, Mind and Matter, the world extended in space and time is but our representation. Direct a quote from Schopenhauer's opening line. He asks, if consciousness creates the observed world, why is your world and my world the same? Answer, because there is only one consciousness. He names his dog Atman, keeps a copy of the Upanishads on his desk throughout his life. This isn't dabbling, this is his worldview. How does this connect to probability and quantum mechanics? Or for Schrödinger, probability in the Born sense is too crude. It suggests the electron has a definite position all along, and we just don't know it. Or it suggests nature is fundamentally random, dice rolls at the basement of reality. Schrödinger rejects both. Instead, the wave function encodes potential observations without claiming the electron is anywhere specific before measurement. The measurement doesn't reveal a pre-existing fact. It doesn't randomly select from pre-existing possibilities. It creates the definite outcome through interaction. But the wave function itself is not subjective. It's not about our knowledge. It's the objective state, but state here means something different from classical states. Not the particle is here with this momentum. Rather, these observation results have these interrelations. Well, the structure of possible experiences, representational but objective. This is exactly what Hugh Everett proposes 7 years later, the many worlds interpretation. But Schrödinger never explicitly says many worlds. He hints at something subtler. The wave function encodes many potential observation records. When you observe, you become correlated with one branch. But this doesn't mean the wave function splits. It means your perspective as an observing subsystem becomes relative to one outcome. The universal wave function still evolves continuously. Other branches still exist in the mathematical structure even if you can't access them after decoherence. Schrödinger is groping towards something like relative state or consistent histories, but without the later technical machinery. They describe how to think about quantum mechanics, but don't provide new equations or testable predictions. Second, the Copenhagen interpretation works. Born's rule makes correct predictions. Physicists are pragmatists. If you can't show your interpretation predicts something different, why adopt it? Third, Schrödinger mixes physics with mysticism. Talking about Vedanta and consciousness alienates his colleagues. They see it as religion invading science. Fourth, his writing style becomes obscure. Bohr's writing is famously impenetrable, but at least commands institutional authority. Schrödinger is in Dublin, isolated, aging. His influence wanes. The Schrödinger equation governs atoms, molecules, chemical reactions, solid-state physics, quantum field theory, modified, extended, reinterpreted, but still central. The mathematical structure he found is unquestionably correct. The measurement problem Schrödinger and Einstein identified remains unsolved. When exactly does superposition end and classical definiteness begin? Nobody knows. Experimental tests keep pushing the boundary, superpositions of larger and larger objects. Molecules with thousands of atoms in two places at once. The cat is still neither fully alive nor dead in the formalism. Modern philosophers of physics read Schrödinger's later work with new respect. Michael Bitball, analyzing Schrödinger's philosophy in 1996, shows the sophistication of his position, not naive realism, not instrumentalism, a representational realism where the wave function is objective, but what it represents is not particles with properties. Rather, it represents the structure of possible observations. This sounds like cubism minus the subjective Bayesianism, or like relational quantum mechanics minus the focus on systems as observers. No ancient text contains Schrödinger's equation. But the philosophical framework, the idea that multiplicity is representational, that ultimate reality is unified, that observation involves consciousness inextricably, this shapes how he thinks about what the equation means. It's not that Vedanta gave him physics. It gave him a way to be comfortable with what the physics was saying. When Born's probability interpretation makes the observer central, Schrödinger can accept that reality depends on representation. But he wants reality itself to be unified, deterministic, complete. The wave function is real and evolves deterministically by his equation. Probability enters only through our limited access as subsystems. It's a sustained attempt to make sense of a theory that defies sense. The experimental facts are clear. Particles interfere like waves. Double-slit experiment. Electron goes through both slits. Interference pattern emerges. But when you detect which slit, the interference vanishes. Observation changes the outcome. How? Bohr says complementarity. Particle and wave are complementary descriptions, mutually exclusive but both necessary. Heisenberg says uncertainty. You can't know both position and momentum. Born says probability. The wave function gives chances, measurements, select outcomes. Einstein and Schrödinger say incompleteness. There must be underlying variables we don't see. Schrödinger specifically says the wave function is complete, but we're misunderstanding what completeness means in this context. John Bell derives his theorem in 1964, published 1966. Bell shows that any local hidden variable theory makes predictions different from quantum mechanics. Testable difference. Alain Aspect performs the experiments in the early 1980s. France. Tests with entangled photons. Quantum mechanics wins. Local hidden variables lose. Einstein's hoped-for completion doesn't work, at least not locally. This seems to vindicate Copenhagen, but it doesn't address Schrödinger's version of the objection. He never proposed local hidden variables. He proposed that the wave function is the complete objective state, but interpreted representationally rather than ontologically in the usual sense. The wave equation is in every quantum textbook. His philosophical objections are footnotes. He continues writing. 1961, January 4, dies of tuberculosis in Vienna, age 73, buried in Alpbach, Catholic cemetery despite not being Catholic. The priest allows it because Schrödinger is a member of the Pontifical Academy of Sciences. His wife Annie survives him by 35 years. His scientific mistress Hilde March keeps his papers. The estate goes to the Austrian National Library. Hundreds of letters, notebooks, working drafts. The philosophical manuscripts are slowly published. Added. The hydrogen spectral lines, Lyman series, Balmer series, Paschen series, all explained. The chemical periodic table explained by electron shell structure. Molecular bonding explained by wave function overlap. Quantum tunneling explained by exponential decay in forbidden regions. Superconductivity, superfluidity, Bose-Einstein condensates, quantum computing, all built on the Schrödinger equation. The wave function PSI is inescapable in modern physics. Term Verschränkung in German. He identified the phenomenon that Bell would later quantify. Two particles described by a single wave function that cannot be factored. Non-separable. This is the technical heart of the EPR argument. It's what makes quantum mechanics genuinely non-classical. Schrödinger saw it clearly. Classical probability is ignorance. You don't know which side of the coin will land up. Quantum probability is structural. The wave function isn't hiding information about where the electron really is. The electron doesn't have a position until measured. But this doesn't mean it's in all positions. It means position is not the right category before measurement. The wave function describes something more fundamental than particles with positions. It describes the space of possible measurement outcomes and their phase relationships. These phases matter. They create interference. Destroy them by measurement, and you destroy interference. Born's rule, probability equals amplitude squared, is how we extract classical probabilities from quantum amplitudes. But the amplitudes themselves are more basic than probabilities. They're complex numbers. They have phase. Probability loses phase information. This is why quantum information theory uses density matrices and pure states. This is why quantum computing works. Interference of amplitudes before measurement. Classical probability can't do that. If quantum mechanics were just probability theory with constraints, quantum computers would be impossible. But they work, in principle. Google claims quantum supremacy in October 2019 with 53 qubits, Sycamore processor. Samples from a probability distribution classical supercomputers can't efficiently sample. The wave function matters. He saw that Born's rule is correct for extracting measurement predictions, but insufficient for understanding the theory. The wave function is not a probability distribution, it's an amplitude distribution. Amplitudes add, probabilities don't. This makes quantum mechanics fundamentally different from classical statistical mechanics. Maxwell and Boltzmann used probability because they couldn't track 10 to the 23rd molecules. That's ignorance probability. Schrödinger's wave function is complete information about the quantum state. But what it's complete information about is not where is the particle, but what will observations reveal and how do they relate? This representational understanding, observations are fundamental, not observed objects, is Schrödinger's genuine contribution to interpretation. He doesn't articulate it with modern clarity. He wraps it in Vedanta, but it's there. Not an ontology of particles in space. Relationalists like Carlo Rovelli argue exactly this. Quantum mechanics describes relations between systems, not intrinsic properties. That's close to Schrödinger's late position. My consciousness and your consciousness are the same consciousness perceiving through different brain structures. Most physicists reject this utterly. They want consciousness to be irrelevant to physics, or at least fully explainable by neuroscience. But the measurement problem refuses to go away. Something about observation, or decoherence, or environment-system interaction selects outcomes from superpositions. Whether you call that consciousness or information transfer or thermodynamic irreversibility, some asymmetry is there. Eugene Wigner later argues consciousness collapses the wave function. His friend paradox, identical to Schrödinger's cat but with a human observer inside the box. If the friend sees a definite outcome but an outside observer sees the friend in superposition, whose perspective is reality? The debate continues. Cubism says both perspectives are valid as assessments of probability. Many worlds says both branches exist. Copenhagen refuses to answer. Schrödinger wanted an answer that preserved objective reality without collapse. All branches of the wave function are real mathematical structures. But consciousness, being unified, experiences one branch, not because that branch is selected randomly, because consciousness does not branch. There is one experiencer seeing one sequence of events, even though the wave function contains many sequences. This is neither Copenhagen nor many worlds exactly. It's a consciousness-mediated relative state. The wave function is objective. Your experience is subjective but not probabilistic. You necessarily experience one definite sequence. Which sequence depends on the phase relationships when your brain state became correlated with the measurement apparatus, which became correlated with the quantum system. But from God's eye view, all sequences exist in the wave function. From your view, one sequence happened. Both descriptions are complete within their domains. This sounds like mysticism, or it sounds like relational quantum mechanics plus property dualism about consciousness, or it sounds confused. Schrödinger never clarified which. Complete probability is not fundamental. He's partially right and partially wrong and mostly prescient. The equation is his monument. The interpretation is his ghost. Kinetic energy is negative h bar squared over 2m times the Laplacian. Potential energy is v of position. This equation is deterministic. Give me psi at time 0. I can calculate psi at any future time. Perfectly deterministic evolution. No randomness. No probability. Then Born says, take the modulus squared. That gives probability. The deterministic evolution produces a probability distribution. Where does the randomness come in? During measurement, the wave function collapses, randomly, unpredictably. One outcome is selected. This two-stage process bothered Schrödinger from day one. The lowest energy is minus 13.6 electron volts. Ground state, n equals 1. First excited state, n equals 2, gives minus 3.4 electron volts. Second excited, n equals 3, gives minus 1.51 electron volts. The pattern is minus 13.6 over n squared. This formula appears in Bohr's model from 1913. But Bohr postulated it. Angular momentum is quantized. MVR equals n times h bar. Circular orbits, arbitrary rules. Schrödinger derives the same formula from a wave equation with no arbitrary quantization rules. The boundary conditions on the wave function: it must be finite everywhere. It must go to 0 at infinity. These boundary conditions select discrete energies. Quantization emerges, not postulated. This is the power of wave mechanics. The wave function decays exponentially from the nucleus. The probability density peaks at the Bohr radius, 0.53 nanometers. But in Schrödinger's model, this is just the most probable radius. The electron can be found closer or farther. This difference matters for tunneling. Barrier penetration. The electron can be found in classically forbidden regions. The wave function is non-zero there. Small amplitude, but non-zero. This explains alpha decay. George Gamow applies wave mechanics in 1928. The wave function tunnels through the barrier. This matches observed decay rates. Pure quantum mechanics. Schrödinger's equation explains it. The probability is derived from the wave amplitude. This distinction matters. Tunneling time experiments are done in the 2010s, attosecond measurements. Results are ambiguous. The measurement problem again. Different wavelengths travel at different speeds. This worried him. But stationary states don't spread. Energy eigenstates maintain their spatial shape. The uncertainty principle is related. Heisenberg derives it in 1927. Delta x times delta p greater than or equal to h bar over 2. This follows from wave packet analysis. Narrow in space means broad in momentum. It's Fourier mathematics. Schrödinger knows this from the start. But Heisenberg interprets it as limitation on knowledge. Schrödinger interprets it as feature of wave representations. Waves don't have definite position and momentum simultaneously, not ignorance. The question isn't well defined for a wave. Born's probability interpretation makes it about ignorance. Schrödinger's wave interpretation makes it about the nature of waves. Different philosophical positions, same mathematics, different ontology. 1927 becomes crucial. April, Heisenberg publishes his uncertainty paper. May, Bohr presents complementarity at the Como conference. Particle and wave are complementary aspects. You see one or the other depending on the measurement, never both simultaneously. This is Copenhagen's core idea. The measurement apparatus determines what aspect appears. No measurement, no definite aspect. October, the Solvay conference. Einstein challenges with thought experiments. Imagine a box with a hole and a shutter. Single photon inside. Shutter opens briefly. Photon escapes. Weight the box before and after. Get the energy from mass-energy equivalence. Time the shutter opening. Get the time. Therefore, energy and time are both determined precisely. Violates uncertainty. Bohr spends all night worrying. Next morning he has the answer. The weighing apparatus disturbs the time measurement. Use Einstein's own general relativity. Gravitational time dilation. The uncertainty in the weight measurement induces uncertainty in the time. When you calculate it carefully, uncertainty is maintained. Delta E times delta T is greater than or equal to h bar over 2. Einstein concedes this round, but he still doesn't accept the interpretation. Neither does Schrödinger. They see the technical victory, but not the philosophical victory. Then particle 2 would have definite momentum. Our free choice of measurement on particle 1 determines whether particle 2 has definite position or definite momentum, but particle 2 is far away. No signal can travel between them faster than light. Therefore, particle 2 must have had definite position and definite momentum all along. Quantum mechanics doesn't describe these definite values. Therefore, quantum mechanics is incomplete. This is the EPR argument. Elegant, compelling, based on locality and realism. Schrödinger immediately writes about it, July 1935. He introduces the term entanglement for Schrenkung. It's the key issue. The two-particle wave function cannot be written as a product of two separate one-particle wave functions. It's entangled, correlated, inseparable. This non-separability is what Einstein calls spooky action at a distance. Schrödinger agrees it's the crux. His cat thought experiment is designed to scale up this entanglement problem. The atom becomes entangled with the detector with the hammer with the flask with the cat. Entanglement propagates to macroscopic scale. The cat is entangled with the atom. Superposition spreads. This is supposed to be absurd, but quantum mechanics says it happens. Bohr responds to EPR in September 1935. Same journal, Physical Review, same title. Can quantum mechanical description of physical reality be considered complete? Bohr says yes. His response is notoriously obscure. He attacks the EPR criterion of reality. They said if you can predict a quantity with certainty without disturbing the system, there must be an element of reality corresponding to that quantity. Bohr says this criterion is ambiguous. The word without disturbing assumes you can separate the measurement apparatus from the system. But in quantum mechanics, you can't. The measurement setup is part of the phenomenon. Change the measurement setup, and you change what is real. Position and momentum are not simultaneously real. Which one is real depends on the measurement context. This is complementarity. Schrödinger and Einstein find this unconvincing. It seems to make reality observer-dependent. Bohr insists it's not subjective. The measurement apparatus is physical, but it's also not objective in the classical sense where properties exist independent of measurement. It's a middle position. Most physicists accept it pragmatically. Schrödinger and Einstein reject it philosophically. Einstein to Schrödinger, Schrödinger to Einstein, 1935 through 1950. They encourage each other. They share frustrations. Einstein works on unified field theory. Schrödinger works on unified field theory. Both are sidelined. Quantum field theory develops in the 1940s. Quantum electrodynamics. Feynman, Schwinger, Tominaga. Incredibly accurate predictions. Lamb shift. Anomalous magnetic moment. Agreement with experiment to 10 decimal places, all using quantum mechanics with Born's probability rule. The Copenhagen interpretation seems validated by success. Schrödinger's objections seem increasingly irrelevant. He's in Dublin, isolated. Physics has moved on. The plurality of bodies versus the singularity of mind. He rejects the idea that each brain generates a separate consciousness. Instead, there's one consciousness experiencing through many brains. This is straight from Vedanta. Is this physics or metaphysics? He claims it's the only way to make sense of quantum mechanics without falling into contradictions. If consciousness collapses the wave function and consciousness is unified, then the collapse is a shift in what the one consciousness is experiencing. Not a physical change, a change in representational perspective. The wave function doesn't physically collapse. Our description relative to our perspective shifts. The universal wave function continues evolving. We experience one branch because we are unified observers. This is very close to Everett's later relative state idea. But Schrödinger doesn't develop it technically. He presents it philosophically and semi-mystically. The physics community dismisses it. The wave nature persists at larger scales than anyone in 1926 imagined. Schrödinger's cat keeps growing. We haven't found the boundary where superposition ends and classicality begins. Maybe there is no sharp boundary. Maybe decoherence is gradual. Maybe we've been asking the wrong question for 90 years. Maybe Schrödinger saw that and couldn't quite articulate why the question is wrong. Maybe probability is the wrong frame because it assumes a fact of the matter about which outcome really occurs, and we're just uncertain. But in quantum mechanics, there is no fact until observation defines the question. Then and only then does probability apply. Before that, amplitudes rule. Phases matter. The wave function is everything. This is what Schrödinger understood. This is what Born's rule implements without explaining. This is what Copenhagen accepts without justifying. This is what many worlds tries to explain by saying all outcomes occur. This is what Schrödinger tried to express through Schopenhauer and Vedanta, because Western philosophy in 1926 had no vocabulary for representation, without realism or non-classical correlation, without causation or observer-dependent reality, without subjectivism. Quantum foundations is a thriving field. Quantum information is an industry. Quantum computers exist in prototype. Quantum cryptography is deployed. Entanglement is a resource. The wave function is inescapable. We still don't know what it means. Schrödinger knew we didn't know. He tried to tell us. We didn't listen. His equation survived. His interpretation didn't. But the interpretation problem survived too. And that problem still carries his name, Schrödinger's cat. The thought experiment that was supposed to show absurdity now symbolizes the central mystery. When does quantum become classical? How does probability emerge? Where's the cut between observer and observed? These are the questions Schrödinger asked in 1935. We still ask them today. He couldn't provide the right vocabulary, but he knew we needed one. Wave function first, probabilities derived, amplitudes not ignorance, representation not realism, observation not revelation, unity not multiplicity. These fragments sketch something that might have been profound if he'd found the math to say it clearly, or something that was profound, and we still haven't found the math to see why. Either way, he saw deeper than Born's rule suggests. He saw that probability was the output, not the explanation. The wave function is input. The Schrödinger equation transforms it. Measurement extracts probability via Born's rule, but the core mystery is what the wave function is, not what probability is. We've been focused on the wrong question. Schrödinger tried to redirect us. His way of redirecting, through philosophy and mysticism, ensured we ignored him. But he was right that we were missing something. We're still missing it. The equation works perfectly. The understanding remains incomplete. The representational view, the rejection of probability is fundamental. The insistence on determinism and objective reality, the defeat by Copenhagen, the vindication by experiments that still show interference, the legacy that is both triumphant and tragic. He gave us the math. We rejected his meaning. The math was enough, except it wasn't. We're still asking what it means. He told us it means something deeper than probability. We still don't know what.